Okay, here we have a solid object. I'm going to put a Bunsen burner underneath. I'm going to heat it up. So the internal energy is going to increase. Let's say it's at minus 10 degrees first. Okay, as I heat up, the temperature will increase, and in fact, it's going to increase up to its melting point, which we're going to say is around 30 degrees Celsius. What's going on? Why does the temperature increase? So at first, the particles are vibrating like this, but as I heat it up to 30 degrees, the particles are going to be vibrating faster. So they've gained kinetic energy. So during this section here, when the temperature increases, it's the kinetic energy of the particles that increases and they vibrate more and the temperature increases. But after you've hit that melting point, the temperature actually remains constant like this. So why is this? Why is it that even though I'm heating it with the Bunsen burner, I'm giving it internal energy is increasing, its kinetic energy and the temperature isn't increasing? It's because all the energy is going into separating the particles like this, overcoming that force of attraction. So during melting, during the change of state, the force of attraction between the particles is weakened. So we're not completely breaking it, we're just making it a bit weaker. And the distance between the particles increases. So actually the potential energy of the particle that increases, not their kinetic energy. So that's why the temperature is still the same. It's still 30 degrees Celsius because they're still moving or moving with the same speed. Okay, let's continue heating up. Now it's a liquid. If we keep heating up from this point, it will increase its temperature again, and let's say increases up to 80 degrees Celsius, which is up to its boiling point. Okay, what's going on right now? So the particles are moving around like this at 30 degrees Celsius, but because the energy they've gained, they're going to be moving faster. Once again, it's the kinetic energy of the particles that's increasing and they're moving around faster while the temperature is rising. But once you hit that boiling point and you continue heating it, temperature remains constant like this. Okay, why is this? Even though we're still heating it, it's because the energy is being used to separate the particles. And this time we're actually completely breaking the force of attraction between the particles, and we're increasing the potential energy a lot, and we're increasing the distance between the particles a lot. So all the energy that the Bunsen burner is giving, the internal energy it's going into it, is used to increase the potential energy part of it, not the kinetic energy part. So the speed of the particles hasn't changed. Now it's a gas. Let's continue heating it. The temperature is going to start increasing again. That's because the particles are going to be moving faster and faster, and the kinetic energy increases. So maybe the temperature goes up to 120 degrees, and then we keep heating up. It goes up to 200 degrees Celsius. The particles get faster, and the kinetic energy increases, and that's what causes the temperature to increase. Okay, so let's summarize this heating curve. During these diagonal sections where the temperature is increasing, it's the kinetic energy of the particles that's increasing. Okay, the average kinetic energy, that's a better word to use. Okay, if it's a solid, we say it's vibrating faster. If it's a liquid or a gas, then we say the particles are moving faster. And that's what causes the temperature to increase. Now, during these horizontal sections where the temperature is constant, it's the potential energy part that's changing. Because during these sections, that's where the change of state is occurring. It's either melting, boiling, and so on. And the distance between the particles is changing. It's increasing in this case. And we're making the force of attraction between them weaker, or we're just completely breaking it. Like, for example, when you turn a liquid into a gas. And it's the potential energy part that's increasing during that section. It doesn't need to be a heating curve, it can also be a cooling curve. So let's take this hot gas, and put it inside the freezer. So at first the particles are going to be moving around really fast, they have high kinetic energy, and the temperature is going to be hot. And then eventually it's going to start cooling down over time. Okay, so that's because the particles will be moving more slowly. And once you hit the boiling point, it's going to condense into a liquid. So the particles are going to come closer together. And during this stage, the temperature won't change. Temperature is constant as it changes state into a liquid. And then once again, the temperature is going to start decreasing as the particles lose their kinetic energy and start moving more slowly. And then once you hit the melting point, once again, it's going to be a change of state. In this case, it's going to freeze into a solid. And then again, the temperature starts to decrease. That's because the particles lose their kinetic energy, are going to move more slowly, or they're going to vibrate less in this case. So during these diagonal sections, the temperature is decreasing because the kinetic energy is decreasing. And so they're moving or vibrating less, and that's what causes the temperature decrease. During these horizontal sections, we call those changes of state. So in this case, condensation and freezing. The potential energy is decreasing during these sections. That's because the particles are moving closer together and the force of attraction is actually getting stronger. the force of attraction is strongest in the solid.